thinking about the early Earth, of course the big question is who was living there at the time? Paleontologists are used to trying to recreate ancient environments and figure out who was living at the time and what ecological interactions were occurring. And they do this using the principles of uniformitarianism. That is, the idea that the modern world is similar to processes that worked in the past. Here in the snowy range of Wyoming, we see an incredible environment preserved from 2.1 billion years ago that sheds a lot of information on ancient life on Earth. Paleontologists use three kinds of fossils to understand ancient environments: body fossils, chemical fossils, and trace fossils. Body fossils are nouns. They're things we're used to, like shells and bones. But when you're looking at the early Earth, there's not many things that are preserved. And those things would be fossilized bacteria. There's a handful of sites that do have exquisite preservation, like the Gunflint Formation in Ontario, which is 1.9 billion years old. In those rocks, a kind of mineral, silica, preserves the bacteria in exquisite detail so that under the microscope you can see all kinds of structures preserved in the cells. Chemical fossils include organic molecules like lipids that get preserved in the rock record long after an organism dies. It also includes isotopic ratios, that is, as organisms use certain elements in the life processes like carbon, then that imparts a change in the ratio of light to heavy isotopes of those elements, which also gets preserved in the rock record. Trace fossils are a category of fossils that are not the organism themselves, but how the organism moves through the environment and changes it that gets preserved. Things like trackways in younger rocks. But on early Earth, trace fossils are stromatolites, these amazing rocks we see here in the snowy range. Stromatolites is the name of a rock that records layer by layer how bacteria interacted with their environment. They may be trapping grains of mud or sand, they may be fostering precipitation of cements, but either way it becomes part of the rock record, and later on geologists can take those stromatolites apart and try to interpret the environment. We know that microbes interact with their environment in many different ways, and that's manifest in the many different kinds of stromatolites we see here in the snowy range. We see an exquisite diversity of forms, including domal structures that expand upwards, sometimes on the scale of many meters. There's also many crinkly laminites, and using those principles of uniformitarianism, we know that the crinkly layered stromatolites most likely formed in an intertidal zone. We also see conical structures, and conical structures are unique because modern experimentation shows that conical structures can only be produced by filamentous microbes migrating up and down the structure. There's also a number of structures here that we have no example from the modern environment and challenges our use of uniformitarianism. In particular, these incredibly large stromatolites that are on the orders of tens of meters tall, but are made up of many small centimeter-sized columns. The final step in trying to understand early life on Earth is putting these stromatolites, or whatever fossils, chemical fossils or even body fossils, into what's known as a Facies model. Geologists gather clues to understand what the environments were like, and facies is a term we use to denote how an environment is preserved in the rock record. And so that includes the organisms, but it also includes the sediments. What are the grain sizes? Were these organisms living in mud, or were they being challenged by coarser sediments? Or sedimentary structures. For instance, were those sediment layers deposited as thin sheets, or do we see them piled up into ripples or wave structures? Do we see cracks? Do we see molds of evaporite minerals that give us a sense of where in the water column these organisms were living, and to give us a sense of what facies we find on early Earth? So developing these facies models and joining that together with this diversity of stromatolite types, piecing that together with atmospheric changes and water changes we can record in the rock record, looking at unique rocks like the banded iron formations and komatiites, and these amazing historical episodes like the Snowball Earth, allows us to create a more full picture of what the early Earth was like.